Hello all and welcome back. So in this video now let us find the time complexity of merge sort. Okay, merge sort is another algorithm which we have done recursively. In this we are given an array. We first divide this array into two parts by middle, right? Is this? So we first divide our array into two parts. Call merge sort on these individual parts and then merge the final output into the same size array, right? So this is the whole process which we do. So merge sort on smaller parts and then we finally do the merge, right? Let us understand this via code as well. So we have the code for merge sort as well in front of us. Now here we are not calling the merge function, rather doing it inside our main merge sort only, so that should be fine. If you will pay attention, what exactly is happening is that I am doing some k work, let's say k1, right? Post that I am calling on my two halves, so I can call this something like this. If the whole is tn, then tn by 2, but I am doing it 2 times, right? So this is something I am doing, and then I seem to work on making the full array, right? Again I am making the full array, which I can maybe say something like this, k to n. So I'm going to do this work, right? This particular work which I'm going to do, here we can have a case like this as well, where left is having all the things and right is empty, something like that, or right is just having a single element. The idea is that this merge function actually does some work, okay, which is equals to dependent on or directly proportional to my n, right, the length of my array, because finally it's actually going to go to each and every element which is present in the left and right, so in left and right, and then work and finally get me the sorted arrays, right? So with that in mind, what we can do is we can write the relation of time again. So pay attention everyone. Yeah, so what I can write is t of n is equals to some work k which I did to find the middle and everything, then 2t n by 2, and then maybe I can combine the whole other work which is, let's say, k2n, something like this, right? Let me call this k1. Okay, if I just try to write it a little bit nicely, what it will become is k plus 2t n by 2 plus k2n. Let me take it k1 again. This particular part will become 0 because if we see, we have a k2n and k1, right? Now again we have seen this multiple times now you should all be a lot comfortable in this. With increasing power, a constant will not have any significance in terms of our n, right? So we take the highest order power. Now if I actually just move forward, okay, we have to make sure. So again, the understanding of merge sort is very important. How we are just doing the k work, how we are calling on two separate halves, all these things is a lot required. I can write my final relation as tn is equals to kn, so I am making this k2 equals to k only, plus 2t n by 2, right? Great. So now if I think with respect to this particular n by 2 array, how I can write this? I can say that t n by 2 is equals to, again I will be doing some k work, but this will be this time on n by 2, right, plus 2t n by 4, n by 2 divided by 2. So if I put n by 2 here, or you can just think in this term as well. So we have this particular array, right, which is n by 2 in length. So I'm just doing n by 2 works now. Again, if I just write it for n by 4, because that n by 2 is going to call another function, another merge sort. It's going to be k n by 4 plus 2t n by 8. This whole all the way to, if I say that, okay, I just have a single element t1, then I can say that I will be doing just some constant work, k, right? If I have just one element, then of course I'm not doing anything. If the length of array is greater than 1, then I'm just returning, so some constant or some just very minuscule work, right? Now again, we cannot add them as it is, because if we are going to add them, just a single t is going to get cut. So what I'm saying is that if we add them, just this will cut with a single, right? So to make sure that we are able to get the final answer, which is our T of n, what we can do is we can multiply this by 2, we can multiply this by 4. So we can do easily, right? We can multiply the each half of the equation, the left and the right half, by the same number. So on that matter, what I'm going to do is I'm going to multiply this by 2, I'm going to multiply this by 4. This 2 is going to get cancelled, this 4 is going to get cancelled, and in a similar manner the next one is going to get multiplied by 8, it's going to cancel this. This will change to 4, this will become 4, this will become 8, and in a similar manner everything is going to get multiplied. Now if we see, if I add this, okay, so again just one more thing I forget, yeah, here 2 is going to come, here 4 is going to come, here whatever it was 8 is going to come, and all the way here, okay. Now if I just add them, we can very clearly see that we are very good to just cancel them out, right? This will get cancelled with this, cancel with this, so it's 4 here and it's 4 here as well, 2 here, 2 here as well, cancel, cancel, right? So now we have done a lot of cancelling, plus in each and every of this equation I will just get k, kn, not k, just kn, right? So how can I write this now, everyone? The way I can write this, if I add them, I hope this was clear the way I've added it, okay, that's a little bit caveat in this problem only, the way you add this. I will be getting Tn is equals to Kn plus Kn plus Kn dot dot dot, how many times? Let's say x, right? This k I am just ignoring because again it's a constant, it won't have any significance in terms of front of kn, right? Now we have to just figure out how many times we will be having this. Again, I think this is the sum problem which we have done already. So if we are dividing our major array into half at every point, right? In binary search we used to just divide it or work on the single half. Here we are just working on 2 half. So with that understanding, what I'm going to get is T of n is equals to Kn plus Kn plus Kn x times, right? n by 2, n by 4 dot 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 1. I have to get how many times I'm taking to reach this. N by 2x is equals to 1. This implies x is equals to, we have seen this already in the binary search, log 2n. If that's the case, then I can just directly say T of n is equals to Kn log 2n. This should be less than equal to my k plus 1 log 2n, and let me remove this, n into log 2n, right? If we do this, then we have our complexity, final complexity, which is going to be O of n log n, right? I can take this as a gn, so that's why. Now again, just one more thing I would like you to think, that first, recursive relation is very important. You should have a proper understanding of recursion if you want to find out the overall complexities like this. Second is that for merge sort, in average, best, or even the worst case, this complexity is going to be the same. I can actually very comfortably say that this is the worst, average, and best case complexity. Because even if you give merge sort a sorted array, it's still going to divide and do all these steps, right? It's still going to divide and do all of these steps. So this is the total complexity of the merge sort. Just one more thing to always remember is that it is of course a lot faster than your other algorithms. We have seen for bubble and insertion sort. You must have done for selection sort yourself as well. All of them were having the complexity as O(n) square, right? And this is O(n) log n. And I have already showcased you that what the exact difference is. When we take n is equals to 1 million, then log n was just coming out to be 20. And that's the exact reason. Now you will be able to appreciate that merge sort was running so quickly here when I was running this, right? But this particular bubble sort, it used to take forever, right? That's the exact reason due to which bubble sort was slower. We were seeing so many time delay when we were getting the answer here. So here we have got the answer, but again, if I'm going to run for bubble sort, maybe I have to wait a lot of seconds, right? This many nanoseconds. So let us see how many time it is. Okay, so let us do 2 seconds, 1492, right? So a lot, basically a lot. 24 minutes. So it has ran on my PC for around 24 minutes and then gave me this result. Whereas merge sort, you can see how quick it was. Okay, so this whole analysis helps you to actually appreciate the algorithm, and now you can understand that why time complexity is important. If for any particular problem you just use bubble sort algorithm instead of merge sort, you can see that how much time it's going to take, right? So I hope now the overall understanding is coming into full circle and you are able to appreciate that why this topic is very important, because in any application, any software, anywhere, time has a role to play, and if we can save that, that's going to actually help us get a lot of benefit. Okay, cool then everyone. So I hope that is clear. Let's meet in the next class. Thank you.